Have you ever stopped to wonder why a campfire feels so warm, but one of those instant cold packs feels, well, freezing? The answer to both is hiding in the energy of chemical reactions. And that's exactly what we're diving into today, the amazing world of thermochemistry. So let's get into it.
So here's our plan. First, we'll get a feel for hot versus cold reactions. Then we'll unpack the two main types of heat. After that, we'll see how scientists actually draw these energy changes and then figure out how they put a real number on it. Finally, we'll see how this shows up in your everyday life and how it helps us choose the fuels that power everything.
All right, let's kick things off with hot reactions, cold reactions. Before we get bogged down in the science, let's just start with something we've all felt.
I mean, this is really the big question, isn't it? How can two different chemical processes have such completely opposite effects? Well, it all boils down to one simple idea. Which way is the heat flowing? Is a reaction pushing heat out into the world, or is it pulling heat in from everything around it?
And that one simple question about heat flow, it leads us straight to the two fundamental types of reactions in all of thermochemistry, exo versus endo. Honestly, if you get these two terms, you've got the foundation for everything else.
Okay, this table lays it all out perfectly. On the left, we have exothermic reactions. Just think exo for exit. Heat is literally exiting the reaction. That's your campfire. It releases energy, so it feels hot, and we give its energy change, or delta H, a negative sign. Now, the real magic is that making new chemical bonds releases a ton of energy, more than it costs to break the old ones. It's like an energy profit. Now, on the other side, you've got endothermic. Endo means enter. Heat is entering the reaction. This is your cold pack. It sucks in heat from your hand, which is why it feels cold, and it gets a positive delta H. It's the exact reverse. It takes way more energy to break the old bonds than the reaction gets back from making new ones. It's an energy loss.
So, how do scientists keep track of all this? It's not just about plus or minus signs. They use these really simple but super useful diagrams to actually map out the energy journey of a reaction.
For an exothermic reaction, just picture a ball rolling down a hill. The starting chemicals, the reactants, are up high, full of energy. As the reaction happens, they release all that extra energy as heat and settle down into the products, which are way more stable and at a lower energy level. That big arrow pointing down, that's all the heat being released into the surroundings.
And here we see the complete opposite. An endothermic reaction is like pushing that ball up a hill. The reactants start at the bottom, low on energy. They have to absorb energy from their surroundings. They need a push just to get the reaction going. And because of that, the final products actually end up with more energy than they started with. That arrow pointing up shows all the energy being pulled in.
But you know, these diagrams are way more than just nice illustrations. Chemistry is all about precision, which means we can go beyond just uphill or downhill and put an actual specific number on the amount of heat involved. To keep things organized, scientists give these energy changes specific names based on the type of reaction. So you have the heat of precipitation for when a solid forms, heat of displacement when metals swap places, heat of neutralization for acids and bases, and a really important one, the heat of combustion, which is just a fancy way of saying burning.
So how do they get that number? Well, they use this incredibly useful formula. Q equals m-c-theta. Q is the heat we're trying to find. To get it, you just need to know three things. M is the mass of whatever you're heating up, which in the lab is usually just water. Theta is the change in temperature. You just measure that with a thermometer. And C, that's a special number called the specific heat capacity. Think of it as how stubborn water is about changing its temperature. It's a constant. You multiply those three together and bam, you know exactly how much heat the reaction gave off or absorbed.
Let's look at a classic example, the heat of neutralization. When you mix a strong acid with a strong base, it consistently releases negative 57 kilojoules of energy for every mole of water that gets made. And a mole is just a standard amount that chemists use, kind of like a dozen. That negative sign confirms what we already know. It's exothermic, it's releasing heat. This number is a solid benchmark in chemistry.
Now, here's where it gets really interesting. What if you use a weak acid instead of a strong one? You always get less than 57 kilojoules of heat. So why is that? Well, think of it like an energy tax. A weak acid doesn't completely break apart in water on its own, so the reaction has to spend some of its energy budget just to rip the acid apart first. And because it spent some energy on that, there's less left over to be released as heat.
All right, let's step out of the lab for a bit. How does any of this stuff actually show up in the real world? You'd be surprised.
These exact principles are behind some pretty clever things we use all the time.
So on the exothermic or heat-out team, you've got everything from those self-heating cans of coffee to the unbelievably hot thermite reaction that welds train tracks together. And of course, the simple act of burning fuel to cook your dinner. Then on the endothermic or heat-in team, we have the classic instant cold packs for sprains and even those cooling gel pads for fevers. They work by literally pulling heat away from your skin.
Okay, so let's zoom out a little. From a single cold pack to the entire planet. How does thermochemistry help us make huge decisions, like choosing the right fuels to run our cars, our homes, and our entire economies?
Well, the most important number here is something called fuel value. It's a really simple idea. How much energy do you get out for every single gram of fuel you burn? This lets us compare totally different fuels, like wood and gasoline, on an even playing field to see which one gives you more bang for your buck, so to speak.
But, and this is a big but, choosing a fuel isn't just about picking the one with the highest fuel value. It's a really tricky balancing act. You also have to think about how much it costs, how easy it is to get, and maybe most importantly, what it does to our environment. A fuel that releases a crazy amount of energy, but also releases a crazy amount of pollution, probably isn't the best choice in the long run.
And that really brings us to the final, most important question. Thermochemistry gives us the hard science, the numbers to measure energy. But deciding how to use that energy, that involves everything from economics to politics to environmental science. So as we move forward, the real challenge isn't just finding the fuel that burns the hottest, but figuring out which fuel burns the smartest for all of us.